Okay, let's dive right back into this. In the first part of this explainer, we looked at why restarting a turbine too soon is basically a death sentence for a hot engine. The hot rotor and the cool casing? Yeah, bad combination. So today, we're going to look at the exact fixes that let you restart safely. But we're also going to uncover a brand new, completely invisible fret. Picture this. Your turbine just tripped. The rotors coast down, the roaring noise stops. Honestly, a lot of operators just breathe a huge sigh of relief. But here's the critical truth. A totally silent, completely dormant machine can still destroy itself, or even fatally harm an operator. Let's look at why. It's incredibly easy to fall into this trap, assuming that a silent engine is automatically a safe engine. We're just naturally wired to associate loud noise with danger, right? But inside a high-performance turbine, the literal second that combustion stops, this chaotic thermal clock starts ticking. The heat doesn't just vanish into thin air, it migrates. So the engine might be officially off, but the environment inside that casing is absolutely anything that's safe. So here's the physics behind why we can't just immediately hit the restart button. Remember that thermal mismatch? When a turbine trips, the relatively thin outer metal casing cools down and shrinks super fast. But that massive internal rotor? It stays glowing hot and expanded. If you try restarting during this thermal mismatch, that shrunken casing is going to physically scrape right against the expanded rotor blades. Total nightmare. To prevent this catastrophic rub, we run what's called a hot restart motoring cycle. Basically, we use the starter to spin the engine without fuel, forcing cool, ambient air through the core to actively shrink that rotor back down to a safe clearance. And you absolutely cannot just guess the timing on this cycle. The magic number here is 5. You have to motor the engine for exactly 5 minutes if you're attempting a restart within roughly 2 hours of a trip. Cutting it short just because, operations is screaming for power back on the grid, that's a guaranteed way to grind your rotor blades straight into the casing. It's literally a 5-minute wait that will save you a multi-month repair. But it's not just about time, it's also about speed. During those 5 minutes, you need to be spinning that gas generator at roughly 2,000 to 2,500 RPM. You actually need that aggressive speed to physically push enough dense, cooling air all the way through the hot section. Hitting that specific RPM mark is exactly what reestablishes those microscopic blade clearances, so you can finally, safely, introduce fuel again. All right, let's test your intuition here with a quick check. Imagine you just had a perfectly normal, clean shutdown. The fuel valves click closed, the engine coasts down, all good. But a few minutes later, you glance at the control screen, and the exhaust temperature needle, which should be dropping obviously, is actually ticking upward. What this means is you have a hidden, active, post-shutdown fire caused by residual fuel leaking into the hot combustor. So, what is your very first action? The answer is completely counterintuitive. You engage the starter and you motor the engine immediately. You don't wait around, and you definitely don't send someone out to investigate the skid. Waiting just lets that hidden fire sit there and bake everything. By spinning the compressor immediately, you're blasting massive volumes of cool air right through the core. You are literally blowing the internal fire out, exactly the same way you'd blow out a candle. So how long do you keep blowing that candle out? Well, you keep motoring the gas generator until the exhaust temperature drops definitively below roughly 400 degrees Fahrenheit. You have to keep actively forcing air through the hot section until you cross that specific threshold. That 400-degree mark is your empirical proof that the fire is totally starved and blown out. Next up, enclosure entry rules. Okay. So we've protected the internal engine parts from residual heat, but now we need to protect the human operators from the lethal enclosure environment itself. Before anyone even thinks about opening that heavy steel door, there is a non-negotiable 4-step entry procedure. First, confirm the engine is off. Third, switch off the ventilation fans. Fourth, station a dedicated observer outside. But the absolute most crucial step is step 2. The CO2 fire suppression system must be mechanically blocked with a physical valve. If you skip this and that system accidentally discharges while you are inside, it displaces the oxygen instantly. We're talking about a lethal asphyxiation hazard in a matter of seconds. Seriously, do not skip step 2. Now, even when the engine is completely off and the enclosure is totally secured, there are still 2 unseen hazards that can permanently destroy the internal bearings inside an unpowered engine. I like to call these the silent destroyers: windmilling and welding. Neither of these looks dangerous to the naked eye, but behind that heavy steel casing, they can absolutely scrap a multi-million-dollar rotor. Let's start with windmilling. This happens when natural chimney effect airflow, pulling up through the exhaust stack, causes the turbine rotor to slowly spin all on its own while it's shut down. So why is this bad? Well, because the main lube oil pump is driven by the engine shaft. So if the engine is officially off, there is zero forced lubrication happening. Think of it like putting your car in neutral and coasting down a 20-mile hill with the engine completely turned off. The wheels are turning, sure, but your unlubricated internal components are basically tearing themselves apart from the friction. And this brilliantly illustrates why we have to draw such strict timeframes around that friction. Slow windmilling, so anything under 100 RPM, is generally fine for up to 2 weeks, because the residual oil film can handle that microscopic creep. But if a strong draft pushes that rotor into fast windmilling, say between 100 and 1,000 RPM, the clock starts instantly. You are strictly limited to 5 minutes max before you start actively scoring and destroying those high-speed bearings. Then we have our second silent destroyer, the welding trap. Look, during an outage, a contractor might just need to weld a simple bracket onto the skid. Sounds completely harmless, right? Wrong. Welding absolutely anywhere near that turbine generator package is heavily restricted and requires meticulous, specialized grounding protocols. Here's why. Electricity will always take the path of least resistance. If a welder just clamps their ground poorly, stray high-amperage electrical currents will travel straight through the turbine shaft and arc directly across the microscopic oil clearances inside the bearings. This arcing causes invisible, microscopic surface pitting on the internal metal. It acts as this silent, incredibly expensive destroyer that just hides there until the very next time you start the machine, hit 10,000 RPM, and that pitted bearing violently tears itself to shreds. So let's lock in a quick mental cheat sheet for all these invisible post-shutdown threats. 1. Prevent rotor rub by motoring for exactly 5 minutes at 2,000 to 2,500 RPM before a hot restart. 2. Motor out any hidden internal fires until your exhaust drops below 400 degrees. 3. Obey the 4-step enclosure lockout, especially mechanically blocking that CO2. 4. Strictly obey those windmilling limits. And 5. Meticulously ground all welding equipment to prevent stray currents from eating your bearings. Okay, so the engine is safely locked out and dormant. The operators are safe, but all this leaves us with a pretty fascinating question. If this engine is completely sealed up, how do we actually definitively know the microscopic health of its internal parts before we introduce fuel for the next first fire? How do we catch that tiny bit of wear before it cascades into a massive failure? Well, that brings us into the incredibly cool world of predictive, on-condition maintenance, which is exactly what we'll be tackling in our next explainer.